Hello dear students and welcome to my YouTube channel. In this video we are going to discuss about the mid-semester examination question paper held at the SIES Graduate School of Technology, Nehru. So as you can see, the question paper is of 20 marks and has a duration of 1 hour. Let us see first each question, let us strategize, and then we can see the detailed solution of everything. In question number 1, there are 5 sub-questions, each carrying 2 marks. Sub-question E is from the module gamma and beta functions, and it is directly based on the topic of gamma functions. Sub-question B, again we have an integration, so we got to evaluate this, and this is based on the same module. It is from the topic beta functions. Sub-question C, find particular integral. So this is based on linear differential equations, wherein we have been asked specifically for the particular integral. Sub-question D is again from the same module, linear differential equation. And question 1E, it is based on differential equations of first order and first degree, and we are required to find the integrating factor. Moving on to question 2. Question 2 is based on the module which deals with differential equations of first order and first degree. And question 3, A and B, they are based on the module linear differential equations with constant coefficients and variable coefficients. So let's get started with question 1A. So to begin with, we are going to first declare the integral as I. So it is integral from 0 to infinity x raised to 1 by 4. And here we have got e raised to negative root of x dx. Now, in the last video that I uploaded on gamma functions, the masterclass, you can find the link of that video on the top right now, or also you can check in the description. We had said that whenever there is going to be a radical in the expression, in the integral, we are going to rewrite that as an index. So since it is root of x, we can rewrite it as negative x raised to half dx. And this looks like the gamma function of type 2, which is 0 to infinity, x raised to m, e raised to negative a, x raised to n dx. And the value of this is given as 1 by n, 1 over a raised to m plus 1 over n, and into gamma of m plus 1 over n. So applying this, we can see that the value of m is 1 by 4 in this case, the value of a is 1, and the value of n is half. So if we apply this result, we get that I is equal to 1 over n, that's half, into 1 over a, that's 1 raised to m plus 1, 1 by 4 plus 1, divided by half, which is n. And over here we will be getting m plus 1 again, so that's half, 1 by 4 plus 1 divided by n, that is half. So the first factor is going to be 2. The second factor, since the denominator, the base is 1, this is going to be 1 into, here we can do a little simplification. So this is going to be 5 by 4 into 2. So this gives us 2 times gamma of 5 over 2. And since the argument of gamma is greater than 1, we are going to use the recursive property, and that is going to be 2 times 3 by 2 times half times gamma of half, which is root of 5. So we have a cancellation for 2 here, so the final value is going to be root 3 over pi 2. So that is the value of I in question 1A. Now let's talk about sub-question B. Now sub-question B is a question which is based on beta function. So again, we are going to start with let I is equal to integral from 0 to 2 x square 2 minus x cube dx, and this is of the type integral from 0 to a x raised to m a minus x raised to n dx. The value of this is given as a raised to m plus n plus 1 times beta of m plus 1 comma n plus 1. Here we have made a slight mistake, so this cube is going to be for the whole 2 minus x. Now if we'll compare this formula with the given expression, we can see that the value of A is 2. The value of M is again 2. And the value of N is 3. So we can say, therefore, I is equal to A, which is 2 raised to M plus N plus 1. So that's going to be 2 plus 3 plus 1 times beta of M plus 1. So that's going to be 3 comma N plus 1, which is 4. So thus we have 2 raised to 6 into beta of 3 comma 4. Now we have got beta of 3 comma 4. So we are going to use the conversion formula from beta to gamma. And that is going to be gamma of 3 times gamma of 4 divided by gamma of the sum, that is gamma of 7. So since each argument of gamma is a natural number, we can use the property that says that gamma of n is equal to factorial of n minus 1. So we get here 2 raised to 6 times 2 factorial into 3 factorial divided by 6 factorial. So this is going to be 2 raised to 6 into 2 into 6 divided by 6 times, 5 times, 4 times, 3 times 2. Now let us see what all cancellations we have. So we can get away with the 6, we can get away with this 2. And then here we have got 4 square, which is 2 square. So this is going to be 2 raised to 4. So we have the value of I as 2 raised to 4 is left in the numerator. So that's going to be 16. And 5 times 3 in the denominator. So we get the value of I as 16 over 15. So that's sub question 1b. Now let's talk about 1c. In 1c, you can see that we are interested in the particular integral. And so firstly, let us call that expression in D, the expression in D as f of D. So we can rewrite the given differential equation as the given differential equation is f of D times y is equal to e raised to 3x, where f of D is equal to d cube minus 2d square minus 5d plus 6. So since we are looking out for the particular integral, the particular integral is given by yp and it is equal to 1 over f of D times e raised to 3x. So in this case, this is going to be 1 over d cube minus 2d square minus 5d plus 6 times e raised to 3x. Now, as per the formula for finding the particular integral, when your r of x, that is the right hand side of the given differential equation, is e raised to 3x, we replace the values of d by a. So in this case, if we put, so basically we want to find out what is f of a. So let's see what f of a is going to be. So please recall that f of d is this expression. F of a is going to be f of 3. This 3 comes from the coefficient of x, and that is going to be 3 cube minus 2 times 3 square minus 5d, which is going to minus 5 times 3 plus 6. So we have 27 minus 18 minus 15 plus 6. You can see that this is 33 and this as well as negative 33. So this is equal to 0. So if it happens that f of a is 0, then we got to differentiate f of d, and we are going to also add a multiplier x in the numerator. So this is going to become x over f dash of d e raised to 3x, and this happens since f of 3 is equal to 0. Now next part, f dash of d is equal to 3d square minus 4d minus 5, and we have e raised to 3x. Again, we are going to continue the same process. We are going to find out what is the value of f dash of d at the point 3. So let us see that. So we have x in the numerator. Then this is going to be 3 times of 3 square minus 4 times 3 minus 5, and here we are going to have e raised to 3x. So this becomes x e raised to 3x divided by, this is going to be 27 minus 12 minus 5. So that's going to be 10. So thus we have that the particular integral yp is equal to x e raised to 3x upon 10. Now suppose say had it happened that the denominator again became 0. So in that case we are going to go for a derivative, means we are going to take another derivative. So we'll be dealing with f double dash of d.
In question 1d, we are required to solve the differential equation which is given by d cube y over dx cube plus y is equal to 0. So the first thing which we are going to do is we are going to write down the auxiliary equation. So the auxiliary equation is in this case it will be d cube plus 1 is equal to 0, and we will be using the formula a cube plus b cube. So therefore the left hand side can be rewritten as d plus 1 times d square minus d plus 1 is equal to 0. This gives us that d is equal to -1, and the quadratic factor can be solved using the quadratic formula. So from here we will be getting that d is equal to -b, which is going to be -1 plus minus square root of b square, that's -1 whole square, minus 4 into a into c, and everything gets divided by twice of a. So this is equal to 1 plus minus square root of -3 divided by 2. So we get half plus minus root 3i over 2. So thus we have the three values of d as -1 and d as half plus root 3 over 2i and half minus root 3 over 2i. Since all the three roots are distinct and we have a pair of complex roots, the complementary function is going to be c1 e raised to -1x plus, for the complex root we have got alpha as half and we have got beta as root 3 over 2. So this is going to be e raised to alpha x, that's going to be half x, c2 cos of beta, that's cos of root 3 over 2x, plus c3 times sine of beta x, that's root 3 over 2x again. Now as you can see that in the given differential equation the right hand side is 0, so this gives us that the particular integral is going to be 0, and since the general solution is sum of the complementary function and the particular integral, and particular integral being 0, we can say that the general solution will only be the complementary function. Thus for the given differential equation the general solution is yg is equal to yc, and that's going to be, the first term can be written as c1 e raised to -x plus e raised to x by 2 times c2 cos of root 3 over 2x plus c3 times sine of root 3 over 2x. So that's the general solution for question 1d. Now let's move on to 1e.
Now in 1e we want to find out the integrating factor of dy by dx plus some expression times y is equal to 1. So this is a linear differential equation, and the standard form of the linear differential equation of first degree and first order is dy by dx plus p of x into y is equal to q of x. So if we will compare the given differential equation, which is this, with the standard linear differential equation, we are going to get that p of x is equal to this bracket 1 minus 2x over x square. So let us rewrite this. So comparing given differential equation with dy by dx plus p of x into y is equal to q of x, we get that p of x is equal to 1 minus 2x divided by x square, and we can simplify this as 1 over x square minus 2 by x. Now for such linear differential equations, the integrating factor is given as e raised to integral of p of x dx. So let us do the integration of p of x dx separately. So consider integral of p of x dx. So that's going to be integral of 1 over x square minus 2 by x dx. Now the integral of 1 over x square is negative 1 over x, and for this it is going to be 2 times log of x. So therefore the integrating factor is e raised to negative 1 by x minus 2 times log of x, and this follows from equation number 1. So we can break this as e raised to negative 1 by x times e raised to negative 2 log x. Now in the second factor we see that there is a log, so we will choose to cancel out the log and the exponent. So we can rewrite this expression, the second factor, as log of x raised to negative 2. So thus we get that the integrating factor will be e raised to negative 1 by x, and the second factor is going to be x raised to negative 2. And we can conclude that the integrating factor is e raised to negative 1 by x divided by x square. So that's the solution for sub-question 1e. Now with this we are done with the first 10 marks. And as you can see, they are not very lengthy numericals. They are quite short if you know the concept and topics nicely. Now in question 2, there are 2 sub-questions, A and B, and we need to solve any one. I'm going to solve both in this case, but simultaneously I wanted to observe that how simple it is and how you can save a lot of time by choosing the correct one to do. Now to begin with 2a, we are given a differential equation, solve something times dx plus something times dy is equal to 0, which looks like m dx plus n dy is equal to 0. And whenever you get an expression of this type, you might be thinking of taking help from exact and non-exact differential equations. So primarily we are going to check whether the given differential equation is exact. So to begin with the solution, we are going to compare it with the general form. So comparing given differential equation with m times dx plus n times dy is equal to 0, we get that the value of m is y 1 plus 1 over x plus cos of y, while the value of n is x plus log of x minus x times sine of y. Now for m, we are going to differentiate partially with respect to the y variable. You can see that the first term is a product of y and 1 plus 1 by x. So 1 plus 1 by x can be treated as a constant. The derivative of y will be 1. And then cos y, the derivative is going to be negative sine y. While we differentiate partially n with respect to x, so the derivative of x is 1 and log x derivative is 1 over x and minus x into sine y, again sine y is a constant, the derivative of x is 1. So as you can see that the two expressions are equal. So since the partial derivative of m with y is equal to partial differentiation of n with x, we can say that the given differential equation is exact. And the solution for exact differential equation is given by integral of m dx. In this we treat y as a constant, and plus integral of terms in n which are free from x, that means they don't contain x, dy is equal to 0. So this is going to be integration of m, and as you can see that m is over here So integration of y times 1 plus 1 by x plus cos of y dx plus integration of terms in n which are free from x. You can see that in n there are 3 terms, and the first term has an x, the second term has an x, and the third term has an x. So we do not have any terms in n which are free from x. So this is going to be integral of 0 dy. Over here we don't have 0. This should be c is equal to c. Now in the first integral we will be considering y as a constant. So we have here integral of y. Since y is a constant, let's bring that out. The integral of 1 is going to be x plus the integration of 1 over x is log of x. Again, plus cos of y is a constant. So this is going to be cos of y into x plus 0 is equal to c. So this gives us x into y plus y into log of x plus x into cos of y is equal to c. So this is the solution of sub question 2a. And as you can see, it was a very simple numerical. So out of 2a and 2b, you will be realizing once I do 2b that 2a is very simple to do. Now let's move on to 2b. So again, similar kind of thing we have. We want to solve a differential equation which looks like m dx plus n dy. So over here, comparing given differential equation with m dx plus n dy equal to 0, we get. So the value of m is going to be y times xy plus e raised to x, which we can simplify xy square plus e raised to x into y. And the value of n is going to be negative e raised to x. Again, like in the previous problem, we are going to differentiate m with y. So differentiating m with y is going to give us 2 times xy plus e raised to x, and differentiating n with x is going to give us negative e raised to x. You can see that the two partial derivatives, that is partial derivative of m with y and n with x, they are not equal. So this implies that given differential equation is not exact. Had it been exact, then we would have went on to write on the general solution directly. Now since this is not exact, we will try and find out the integrating factor, and that is going to give us the solution. If you can recall that there are 4 types in which we can find out the integrating factor and only one is applicable. So to choose that, it is going to be slightly trickier. So most of the cases you have to start from type 4, wherein your differential equation must look homogeneous, and here we can see that the differential equation is not homogeneous as it has e raised to x term in it. In the third type, the differential equation must be of the type f1 of xy times x plus f2 of xy times y is equal to 0. So again, this criteria fails. So we are left out to make a choice between type 1 and type 2. So for that, we are going to take the difference. So consider the difference between partial derivative of m with y and the partial derivative of n with x. So when we do this, we have 2xy plus e raised to x. That's the value of partial derivative of m with y, and then we need the partial derivative of n with x. So this is going to be e raised to x. So as you can see, we can factor out 2, and this is going to be xy plus e raised to x. Now for the next part, what we are going to see is whether dividing this expression by m helps us getting a function of only one variable, or dividing this by n gives us the same thing. So in this case, you can see that the function m has one factor which is xy plus e raised to x, and the same factor is over here. So if we happen to divide by m, then this expression will reduce to a function of y variable alone. So we have here partial derivative of n with x minus partial derivative of m with y divided by m is equal to, now since this was partial m with y minus partial n with x, we have to introduce a negative sign. So negative 2xy plus e raised to x divided by m, which is y times xy plus e raised to x. So this goes away and we have negative 2 by y, which is a function of y variable only. Since this is a function of y variable only, the integrating factor is going to be e raised to integration of g of y dy, and that is e raised to integral of negative 2 over y dy, which is e raised to minus 2 log y, and therefore the integrating factor is 1 over y square. Now next we are going to multiply the given differential equation by the integrating factor, and we are going to get y times xy plus e raised to x divided by y square dx, then minus e raised to x divided by y square dy is equal to 0. This differential equation is exact. We state this without any verification, and because that is the job of integrating factor. Whenever you multiply a differential equation by its integrating factor, the resultant differential equation has to be exact. And since we are claiming that it is exact, the solution is integration of m dx. Now instead of saying m, we'll say m prime. And this here, the y has to be treated as a constant, and plus integration of terms in n, so that's going to be n prime free from x dy is equal to 0. So this is going to be integration of, you can see that we can get away with this, and the first term is going to be x alone plus e raised to x over y dx, plus again there is only one term in n prime, and that contains the exponent in x. So here we will be having integral of 0 dy is equal to c. So this is going to be x square by 2 plus e raised to x by y plus 0 is equal to c, and therefore we can say that the solution is x square by 2 plus e raised to x by y is equal to c. Now moving on to the last question, question 3. Question 3 is based on the module higher order linear differential equations with constant coefficients and variable coefficients. So in the first one, we are given a second order linear differential equations. And as you can see that the right side, that is r of x, is not equal to 0. So we are going to find out the complementary function and also the particular integral. So we are going to break down our solution into some steps. So firstly, we are going to find out the complementary function. So to find the complementary function, we begin with the auxiliary equation. So the auxiliary equation in this case is d square plus 2 is equal to 0, and solving this is going to give us d is equal to plus minus square root of 2i, which is actually 0 plus minus square root of 2i. So thus the complementary function yc is e raised to 0x times c1 cos of root of 2x plus C2 sine of root of 2x. Now for the next part, we are going to find out the particular integral. Now the particular integral is given as yp is equal to 1 upon f of d into r of x, where f of d is the auxiliary equation, so that's going to be d square plus 2, and r of x is the right side, which is x plus e raised to x minus cos of 2x. So we can say that yp is 1 over d square plus 2 times x plus e raised to x minus cos of 2x. So this can be broken into three simpler expressions. So this is going to be 1 over d square plus 2 of x plus 1 over d square plus 2 of e raised to x minus 1 over d square plus 2 of cos of 2x. Now these are three different types. So the first part is of the type x raised to m, the second one is of the type e raised to ax, and the third one is of the type cos of a raised to x. So let's do them simultaneously. So for x raised to m, we need to rewrite the f of d as the constant term must be 1. So for that we are going to factor out the 2. So in the denominator, let us factor out 2 and also rewrite this, changing the order. So this is going to be 1 plus d square over 2. And here we have x plus. For exponent, we are going to simply replace the value of d by a. And if it is non-zero, then we are done. In this case, if you see, the value of a is 1. So this is going to be 1 square plus 2 in the denominator. And here we will have e raised to x. And the denominator evidently is not a 0 value. Now coming this side, the value of a is 2, and since we have got a d square here, we are going to replace d square by negative of a square, that is negative of 2 square. So we have the denominator set up, and this is going to be cos of 2x. We have half here, the other term is 1 over 1 plus t square by 2 into x, then this is e raised to x by 3, and over here plus cos of 2x, and the denominator is going to be 2. Now for the first term, we have got this expression. So over here we are going to use the series 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed and so on. So doing that, we get this as half 1 minus t square by 2 plus t raised to 4 by 4. I will not write down entire series. As you can see that the power on x is 1, and if we take the second derivative of this, it is going to give us 0. So already over here we have got the fourth derivative, and writing out down higher order derivatives will not make any sense because these terms are going to be all 0. And here we have e raised to x over 3 plus cos of 2x over 2. So again, we have got half here. Now 1 times x is x. Now minus d square, that's the second derivative of x. And as discussed, the first order derivative of x will be 1. And if we go on for the second order derivative, it is going to be 0. So we have got this expression over here, plus e raised to x over 3 plus cos of 2x over 2. So thus we have that the particular integral yp is x by 2 plus e raised to x by 3 plus cos of 2x over 2. So since we have both the complementary function as well as the particular integral, we can find out the general solution of the higher order linear differential equation. And the general solution is yg is equal to yc plus yp. So that is going to be e raised to 0x is going to be 1 over here, e raised to 0x, that's going to be 1. So we can choose not to write that. So c1 cos of root of 2x plus c2 sine of root 2 of x plus x by 2 plus e raised to x by 3 plus cos of 2x by 2. Now on to the last numerical 3b of this video and also of the MSE examination. So question 3b, and you can see that the question clearly mentions that you need to apply the method of variation of parameters. Now even if it is not said, then how do you decide whether we need to apply the method of variation of parameters to solve this? You need to look at r of x, and r of x is none of the standard types that you have studied. So it's not only exponential, it's not only sine, cos or hyperbolic sine, cos, and it's not only polynomial. So since it's a mix of few things which we haven't done, we are going to apply the method of variation of parameters. Now the method of variation of parameters involves more number of steps compared to the problem which we did just before. So let's again start with finding the complementary function first. So first we find out the complementary function. So for the complementary function, again we are going to need the auxiliary equation. So in this case, the auxiliary equation is d square minus 4d plus 4 is equal to 0, which is d minus 2 whole square is equal to 0, and this gives us that d is equal to 2. So therefore the complementary function is yc is equal to c1 plus c2x times e raised to 2x, which we can also rewrite it as c1 e raised to 2x plus c2x into e raised to 2x. So thus we have the complementary function. Now from the complementary function, we need to extract the two other functions y1 and y2. So here we can say that y1 is equal to e raised to 2x, which is the multiple of c1, and then y2 is equal to x times e raised to 2x. Now moving further, we are going to find out the Wronskian of y1 and y2. So the Wronskian of y1 and y2 is given as the determinant of y1, y2, y1 dash and y2 dash. So that's e raised to 2x, x e raised to 2x, and the derivative of y1, that is e raised to 2x, is going to be 2 times e raised to 2x. And for this we need to apply the product rule or the UV rule. So this is going to give us 2x e raised to 2x plus e raised to 2x. Now evaluating the determinant, we get e raised to 2x times 2x e raised to 2x plus e raised to 2x minus, and then taking b into c, so we will be having x e raised to 2x times 2e raised to 2x. So this first term is going to be twice x e raised to 4x plus e raised to 4x minus twice x e raised to 4x. So we can cancel out this. So you can see that the Wronskian of y1 and y2 is equal to e raised to 4x. So once you have the Wronskian, you need to find out the function u. So the function u is given as negative integral of y2x into r of x divided by the Wronskian. And as you can see, y2 is this. So this is going to be negative integral of x e raised to 2x times r of x. R of x is over here. E raised to 2x into sec square x divided by the Wronskian, which is e raised to 4x dx. So since the denominator has e raised to 4x, we can get away with this. So this reduces to negative integral of x sec square x dx. Using the integration by parts, this is going to be negative x. Integral of sec square x, which is tan of x, and then minus integral of 1 into tan of x dx. So this is negative x tan x minus integration of tan of x is log of sec x. So this becomes negative x tan x plus log of sec x. Now likewise we need to find out the function v of x. It is given as integral of y1 times r of x divided by the Wronskian. So this is going to be, now y1 you can see it is e raised to 2x. So this is e raised to 2x times r of x is e raised to 2x into sec square x divided by the Wronskian, which is e raised to 4x dx. And again we can cancel out this. So we are left out with integration of sec square x, and that is nothing but tan of x. Since we have got u and v, now we can talk about the particular integral. The particular integral is given as u times y1 plus v times y2. So that's going to be negative x tan of x plus log of sec of x times y1. y1 was e raised to x plus v, which is tan of x, times y2, which is x times e raised to 2x. If we simplify the first term, we'll be getting negative x times tan x times e raised to 2x plus e raised to 2x times log of sec x plus over here x times tan of x times e raised to 2x. So this first term and the third term we can cancel. So we get that the particular integral is equal to e raised to 2x times log of sec of x. So since we have got both, now we are in a position to talk about the general solution. So since the general solution is the sum of the complementary function and the particular integral, we can say yg is equal to c1 plus c2x e raised to 2x plus e raised to 2x times log of sec of x. And as you can see that e raised to 2x is a common term, so we can take it out. So we'll be getting c1 plus c2x plus log of sec of x. So with this we complete the MSE paper of February 2026. You can see that the paper was not that difficult if you knew the things, and always make better choices. So there are, in question 2 and question 3, there is one problem which is very simple and easy to do and less time consuming, wherein the other one is comparatively difficult and consumes more time. So if you are smart enough, you should be able to judge that quickly and save a lot of time. Now with this, we'll be stopping this video. I will be attaching relevant cards on, so you can access it from the top right by clicking on the I button. And also I will be attaching the relevant links of the YouTube videos that I have already uploaded. So with this, thank you everyone for watching till the end. And if you have not yet subscribed to my channel, then do subscribe and share this video with your friends who are preparing for MSE examination and have relevant topics. Thank you so much once again, and a very happy learning.